Welcome to video lecture on analog and digital electronics. In this session, we'll study about sequential parity checker and how to draw state table and graph. So today we'll discuss about sequential parity checker. So the counters we design go through a fixed sequence of states and have no input other than a clock pulse that causes the state to change. So we have discussed about counters where clock is the only input. Depending on the clock pulse, counter sequences changes. So, if we consider sequential circuits can have additional input other than clock. So, in order to analyze the sequential circuit that have additional input other than the clock, we need state table and state graph. So, we'll learn how to draw state table and transition graph for sequential circuit. Given a sequential circuit and an input sequence, we analyze the circuit to determine the flip-flop state sequence and the output sequence by tracing zeros and ones through the circuit. We can determine the output and state sequences from the graph and table. So, this graph and table are helpful in analyzing and designing the sequential circuit. So, first let us see what is parity checker. Parity checker is a circuit which is used to check the parity bit in the given sequence of zeros and ones. First let us say what is even parity. Even parity means n bit input has even number of ones. So, if you have n bit input number, then if there are even number of ones in the given sequence, then it is even parity. If there are odd number of ones in the given sequence, then it is odd parity. So, parity is the additional bit which indicates number of zeros and ones in the given sequence. For example, if you see the number 110011, then there are 4 ones. 4 means even, so it is a even parity number. Odd parity means an n bit input has an odd number of ones. If we see the example 111001, it has odd number of ones, hence it is a odd parity number. So, we will see few more example. So, here the numbers are given 4 ones, 40, 4 ones, 00, 11. So, count number of ones in the given sequence. Number of ones in the given sequence is 10, which is even number, hence it is a even parity number. If you see the second number, 4 ones followed by 4 zeros followed by 4 ones and 0111, there are 11 ones in the given sequence, hence it is a 11 is a odd number, hence it is a odd parity number. A parity bit is a single bit that can be appended to a binary string or sequence. A parity bit is also known as check bit. What is the use of parity bit? Parity bit is simplest form, it is used to detect the error, that is 1 bit error in the given sequence number. Parity bit is used to detect 1 bit error in the given sequence of number. So, even the parity bit is additional bit appended to the binary sequence, which can be either 1 or 0. If you append 1, it means it is a odd parity, and if you append 0, you have to write it is a even parity number. So we'll see some example for parity checker, that is odd parity. So I want to make this number as a odd parity number. So we'll see how the parity bit or parity checker is used to detect one bit error in the given sequence. So when the sender sends the information to the receiver, they will agree that they send only odd parity numbers to the receiver. What happens at the receiver side if he receives the even parity number? That means there is a change in one bit, because we receiver knows that every time the sender is going to send the odd parity number. So if he receives the even parity bit, then he assumes that there is a change in single bit. So if there are more than one bit is going to change, then the receiver will not come to know, because if there is two parity bit change, the resultant can be odd parity number. Then he will not notice the change in the bit. If sender and receiver agree to send and receive the odd parity number, when the receiver receives an even parity number, that means there is a change in one single bit. So how can you convert a given sequence of number to odd parity number? So see the example, first line, 000, that is there are 7 zeros. When he sends, the sender has agreed that he is going to send odd parity number. How can he make the 7 zeros into odd parity number? If he append 1 to the sequence of number, then it becomes a odd parity number. So similarly, if the information is 6 zeros followed by ones, how can he convert that number into odd parity number? By appending 0. So see the third example, 011, 011, 0. So it is an even parity number. How can we convert this even parity number into an odd parity number? By appending 1 to the given number. Now what is, after appending 1 to the given number, what is the parity of the number? The parity of the number is odd. If I see the next example, 10101001, what is the number of ones in the given sequence? There are 4 ones. 4 ones means it is an even parity number. How can we convert this even parity number to an odd parity number? By appending an 1. If I append 1 to the given sequence, what happens? There are 5 ones in the given sequence, which is a odd parity number. If I see the next example, 0111000, what is the parity of the given number? It is odd parity. So how can I make this as even odd parity number? By appending 0. So every time the sender is going to send 8-bit odd parity number to the receiver. If any single bit in 8 word is changed from 0 to 1 or from 1 to 0, the parity of the sequence is no longer odd. This will help the receiver to identify single bit error in the sequence. So this parity checker is helpful in detecting single bit error that occurs during the transmission. Now we'll look into sequential parity checker. We can see the block diagram of the parity checker here. So you have a parity checker circuit. Input to the circuit is X, that is sequence of ones and zeros. Z is the output, and you have a clock. Clock means it is a sequential circuit. Sequentially zeros and ones will enter to the parity checker circuit, and Z calculates the parity of the sequence of inputted number. Now, so how this will work? Initially, the x is equal to 0. Suppose if I take x is equal to 0, parity checker will check the parity of the given number. What is the parity? It is a odd even parity, right? So what is the Z value? Z value will be 0. So here the parity checker circuit will remember the parity of the previous state. So parity of the previous state is 0. So parity checker circuit will remember the parity of the previous sequence. Suppose if I add after zeros, if I add next bit is 1. Now what is the parity of 1 0? Parity of 1 0 is 1, right? So the parity of current number is 1. So the current output Z is 1. Suppose if I add one more number, so the input will be fed to the parity checker sequentially by 1 bit, and the parity checker will calculate the parity of the sequence of number, and Z is the output parity bit. So when each clock pulse changes, the parity checker is going to update the parity bit value and it is going to output the parity bit value. Now, so what is the waveform for parity checker? So X is the input. See here, you have clock as one more additional input and Z is the output. Z is equal to current state of the parity checker. So when X is equal to 1, when the clock pulse is given to the circuit, the 1 is fed to the parity checker. So what is the parity bit value now? Parity bit value is 1, right? So initially when no number is fed to the parity checker, the parity value is 0 here. So we know that the output is available in the next clock pulse because of the delay in the sequential circuit. So when you input X is equal to 1 and you give a clock pulse, the output will appear. So the output of this X is equal to 1 will appear here. So what is the parity bit? 1. If I feed 0, next bit is 0. What is the parity of 1 0? It is 1. So next once again I will feed one more 0 to the parity checker. What is the parity of 100? It is 1. After that I will feed 1. What is the parity of 1001? It is 0. Again if I feed 1, what is the parity of 1001? 1, 1. So here for calculating the parity output, we need the previous state of the parity checker circuit. So hence it is a sequential circuit. Now we know one form of representing the circuit is truth table, or you can understand the sequential circuit by waveform also. There is one more way of understanding or analyzing the sequential circuit, that is state graph. So how to draw the state graph? We have studied how to draw the state graph for truth tables, right? Like flip-flops. We have learned how to draw the state graph for flip-flop. Now we'll learn how to draw the state graph for sequential circuit. So what are the two different states of this parity checker? So output can be 0 or 1. So there are two states, Z is equal to 0 and the second state is Z is equal to 1. We'll represent Z is equal to 0 as S0 and Z is equal to 1 as S1. Now, if the current state is Z is equal to 0 and if I feed or if I give X is equal to 0 as the input, what is the next state? Z is equal to 0, right? So it will remain in this particular state itself, which is represented by this loop. X is equal to 0. The next state of the sequential parity checker will be S0. What happens if the current state of the sequential parity checker is Z is equal to 0 and if I feed X is equal to 1, what happens? What is the next state of sequential parity checker? Next state of sequential parity checker will Z is equal to 1, which is represented by S1. Now, the current state of sequential parity checker is equal to S1 or Z is equal to 1, and if X is equal to 0 is the input for the next state. What will be the next state of the sequential parity checker? Next state of the sequential parity checker will be S1 itself. So, currently parity bit is 1 and if I feed 0, what is the parity of 1 0? Parity of 1 0 is also 1. So, it will remain in S1 itself. And the current state of sequential parity checker is S1 or Z is equal to 1, and if the input X is equal to 1 will be fed into the sequential parity checker, what is the next state? So, Z is equal to 1 and next input is 1. What is the parity bit of 1 1? Parity bit of 1 1 is 0. Hence, the next state of Z is equal to 1 and input is equal to X is equal to 1. So, next state will be Z is equal to 0 or S is 0. So, this is the state graph. So, same waveform I have represented in the form of graph. So, this is the block diagram of sequential parity checker using T flip-flop. So, in order to store the current state of the flip-flop, current state of the sequential circuit, I should have some flip-flop or memory. Memory is nothing but a flip-flop. So, here I have used T flip-flop. Hence, it is a sequential parity checker using T flip-flop. You can use D flip-flop or JK flip-flop or SR flip-flop. But here I have used T flip-flop. And this is the state graph for parity checker which we have drawn earlier. Now, from the state graph, we have to derive the state table. So, now let us see how to derive state table from state graph. So, in the state graph, we are going to represent the present state, next state and present output. So, what are the states possible for sequential parity checker? There are only two states, that is S0 and S1. So, present state can be either S0 or S1. Now, we have to represent the next state. Next state depends on the input X. X can be 0, X can be 1. So, when X is equal to 0, what is the next state? When X is equal to 1, what is the next state? We are going to represent in the form of table. And what is the present output? So, S is equal to 0 is the present state. What is the present output? 0, right? If present state is S0, what is the output? Z is equal to 0. So, present output will be 0. If the present state is S1, what will be the output? Z is equal to 1. So, present output is 1. Understood how I have written present state and present output? It's very simple. There are two states, S0 and S1. So, present state will be S0 and S1. Present output. When S is equal to 0, what is the output in the state graph? Z is equal to 0. So, 0. When S1 is the present state, what is the output? Z is equal to 1. So, in the present output, I have written 1. Now, we have to write the next state. So, see the diagram. S is equal to 0 and if the input is equal to X is equal to 0, what is the next state? S0, right? I have written S0. Similarly, if the present state is S0 and the input is X is equal to 1, what is the next state? S1. So, next state is S1. Similarly, look the diagram here. If the present state is S1 and if the input is 0, X is equal to 0, what is the next state? S1, right? So, I have written S1. If the present state is S1 and the input X is equal to 1, what is the next state? S0, right? S0. So, This is how we write the state table. Now we have to see how to write the transition table. So in the transition table, we are going to write how we are going to implement the particular sequential circuit. We are going to implement the sequential circuit using T flip-flop. So we have additional two more columns, x is equal to 0, x is equal to 1 for T flip-flop. So other entries are same. How will you represent present state? Present state is represented by Q. How will you represent the next state? Next state is represented by Q plus. So here I have represented in the state table we are going to write the present state, that is present state, next state as it is. But in the transition table we are going to represent state table, that is we are going to represent the state table in terms of symbols. Present state is represented by Q, next state is represented by Q plus, state S0 is represented by 0, state S1 is represented by 1. Output, that is present output, is represented by Z. So in the transition table is the symbolic representation of state table. So see S0 0, S1 1. So wherever S0 is present in the state table, I write 0. Wherever S1 is there in the state table, I write 1. So S0 0, S1 1. When x is equal to 0, it is S0, so I have written 0. When x is equal to 0 and q is equal to 1, it is S1 here. So see here, S0 I have written 0. S1 I have written 1. Wherever S1 is there I have written 1. Wherever S0 is there I have written 0. Output, it remains the same. Present output I have written Z. Present state I have written Q. Next state I have written Q plus. You can see additional two columns, T x is equal to 0, T x is equal to 1. So here let us recall the truth table of T flip-flop. So let us recall the truth table for T flip-flop. T can be 0 0 1 1, when Q can be 0 1 0 1. What is Q plus? So when T is 0, Q is equal to 0, Q plus is 0. When T is 0, Q is 1, Q plus is 1. When T is 1 and Q is equal to 0, Q plus will be 0. When T is 1 and Q is 1, next state will be 0. Here, sorry, here when T is 1 and Q is 0, output will be 1. So this will be the truth table. So if you recall the truth table, I have expanded T flip-flop truth table. So here, see, when Q is 0 and T is 0, see here, when Q is 0 and x is equal to 0, what is T value? So Q is equal to 0 and the input is also 0. What is next state? 0, right? See here, Q is 0, Q is 0 and x is equal to 0. See here, x is nothing but T here. X is nothing but T here. When T equal to 0, what is Q plus? It is 0. Once again, concentrate. See here, when Q is equal to 1. So Q is equal to 1 and x is nothing but it is input. Input is nothing but T here. T is 0. What is the output? Output is 1. So we have to write depending on the input and output. Similarly, q is equal to 0, x is equal to 1, output will be 1. When q is equal to 1 and x is equal to 1, output will be 1. So, this is the state transition table for sequential parity checker. Now, let us see what is state table and state graph. The transition table and state table for the sequential circuit specify the next state and the output of the circuit in terms of present state and the input. So, remember the definition: state table and state transition table specify the next state and the output in terms of present state and the input. A state in the transition table is specified by the flip-flop output values corresponding to the state. A state in the state table is specified symbolically. I have told. See here, in the case of transition table, I represent the state symbolically. Given a transition table, a state table for the circuit is derived by assigning symbol to the state. The design process for sequential circuit reverses the process. So, usually state table is determined first, then the transition table. See here, first I derive the state table, then the transition table. Now, we will see what are the steps to derive the state table and state graph. So, first you have to determine the flip-flop input equation and output equation for the given circuit. A circuit will be given containing the set of flip-flop of particular type. First, you have to determine the flip-flop input equation and output equation for the given circuit. From the circuit, you have to derive the equation. Second step, you have to derive the next state equation using the equation, that is flip-flop equation. We have derived the equation for flip-flop. For D flip-flop, Q plus is equal to D. For T flip-flop, Q plus is equal to T XOR Q. For SR flip-flop, Q plus is equal to S plus R bar Q. And for JK flip-flop, it is Q plus is equal to J Q bar plus K Q. This we have derived in the previous session. So, we have learned in the previous sessions, we have learned the equations for flip-flop. One way of representing the flip-flop is logic diagram. One more way is truth table. Next way is state transition diagram. Next is using equation. Next one is using excitation table. So, there are various representation for flip-flop. Next, we have to plot a next state map for each flip-flop. Then you have to combine this next state maps to get the transition table. So, we will understand how to derive state table and state graph by taking up an example. So, question is given, derive the state table for the following circuit. A circuit will be given to you. You have to derive the state table or transition table for the given circuit. What is the first step? First step, you have to determine the flip-flop input equation and output equation from the circuit. So, what are the input here? dA and dB are the input. So, see the circuit diagram carefully. dA and dB are the input. A and B are the output, and final output is Z, right? Final output is Z. So, we have to, first step, we have to write the input equation for the flip-flop as well as output equation. Here output is Z, final output. I am talking about final output is Z. So, what is the input? dA. dA is nothing but X XOR B bar, right? And dB is equal to X or A. What is Z? Z is equal to, see here, A XOR B. Z is equal to A XOR B. So, first step in deriving state table and state graph is determine input flip-flop equation as well as output equation. See here, dA is equal to X XOR B bar, dB is equal to X or A, that is X plus A, Z is equal to A XOR B. Same I have done. Now, you have to, what is the next step? Second step is derive the next state equation. So, here which flip-flop is used? D flip-flop is used. So, see here A plus, what is A is equal to? A is equal to X XOR B bar. So, what is A? We know that for D flip-flop, we are using D flip-flop. So, what is the equation for D flip-flop? Q plus. Q plus is equal to D in general. So, here see the first flip-flop. First flip-flop we have named it as DA. What is A? A is equal to DA. What is dA? Previously we have learned that dA is equal to AX XOR B bar. Similarly, we have to write the equation for B. What is B? B is equal to dB. So, dB is nothing but X plus A. So, let us recall the steps. First step, we have to determine the flip-flop input equation and output equation. So, here the input are dA, dB and output is Z. We have written the equation. In the next step, we have to write the next state equation for the flip-flop. So, here there are two flip-flop A and B. For A, it is equal to dA. dA is nothing but XOR B bar. For B, B is equal to dB. So, we know, see here, for D flip-flop, Q plus is equal to D. So, what is D here? There are two flip-flop. I have differentiated two flip-flop as DA and DB. So, B is equal to DB, X plus A. Now, what is the third step? Third step is plot the next state map for each flip-flop. So, there are two flip-flops. So, there will be two maps. So, how to draw the maps? See the diagram. There are two inputs A and B and one more input called X. So, what are the input? A, B and X. What is the output? Z. So, there are two flip-flops. For the first flip-flop, A, B and X are the input. For the second flip-flop, A, B and X are the output, are the input. Output is A plus and B plus respectively. Now see the diagram. Now A, B and X are the input. So, there are three inputs. So, hence I have to draw three variable K map. So, here I have written two variable along the row and one variable along the column and I have written the output. So, how to write the output? So, we have to write the truth table. In order to write the map, we have to write the truth table or directly you can write. So, I will show how to write directly. So, when see here, what is this state? When A equal to 0, B equal to 0, X is equal to 0, what is A plus value? This particular cell indicate what is the A plus value when A equal to 0, B equal to 0 and X is equal to 0. So, see the circuit. Here what happens when A equal to 0, B equal to 0. When B equal to 0, what is the B bar value? 1 and X is equal to 0. What will be the output? 0 XOR 1. Output is 1. So, what will be the A plus value? A plus value equal to 1 now. So, I have written 1. Now, what is the next cell means? Next cell means when a equal to 0, b is equal to 1 and x is equal to 0, what is a plus value? So what happens? See the circuit diagram. When a equal to 0, b equal to 1. When b equal to 1, b bar will be 0 and x is equal to 0. So what is dA? dA is nothing but x XOR b bar. So 0 XOR b bar is 0. So 0 XOR 0 is 0. What is a plus? A plus is nothing but dA. dA is nothing but 0 now. See here in the map also I have written 0. Similarly, when a is 0, a is 1, b is 1, x is 0, what will be the a plus value? When, or you can directly use the equation, what is a plus? A plus is nothing but x XOR p bar. Now current input is a is 1 and b is 1. What is b bar? B bar will be 0 and x is 0. 0 XOR 0, it is 0. Now next state, when a is 1, b is 0 and x is 0, what happens? When a is 0, a will not affect a plus. Now x is 0, 0 XOR, what is b bar? B is 0, b bar is 1. 0 XOR 1, it is 1. Similarly, we have to fill remaining cells. So, how will you fill this value? So, a plus is equal to x XOR b bar. X is nothing but 1 here XOR, what is b value? B value is, here b value is 0. What is b bar? 1. 0, 1 XOR 1. What is value? 1 XOR 1 is 0. Similarly, how can you fill b plus? B plus is nothing but b what is b plus? B plus, what is the equation for b plus? Equation for b plus is nothing but a plus x or a or x. So we are going to apply this equation for all the possibilities. AB x can be 0 0, 0 0 1, 0 0 1 0, etc. So b plus is nothing but a plus x. So what is b plus now? B plus is equal to a plus x. 1 a is 0 and x is 0. What happens to b plus? 0 plus 0, 0. Here when a is 0 and x is 0, 0 plus 0, 0. Here a is 1 and x is 0, 0 plus 1, 1. Here plus means OR operation. A is 1 and x is 0. So a 1 XOR 0, 1 or 0, 1. Similarly, here when a is 0, x is 1, b plus will be 1. When a is 0, x is 1, b plus will be 1. Similarly, when a is 1 and x is 1, b plus will be 1. When a is 1 and x is 1, b plus will be 1. So, this is the table. What is the next step? Next step is you have to combine the maps to get the transition table. So, how will you combine the table? See here, when AB is 0, x is 0, what is A plus? This is A plus entry, this is B plus entry. See here, A plus entry in the first cell is 1. In the second table, B plus entry is 0. So combine 1 0, 0 0, 0 1, 1 1. So when x is equal to 1, 0 0, 0 1, so I am going to combine these two. 0 1 here, 1 1, next 1 1 and 0 1. So you have to combine these two tables. How will you combine? Think that you have keeping the table 1 over 1. So whatever the value of this particular cell 1, first you have to write the cell 1 value 1 0, cell 2 value 0 0, cell 3 value 1 1, cell 4 value 1 1. Next the second column 0 1, 1 1, 1 1, 0 1. So what will be the output then? So what is Z? Z is nothing but A plus B. So A plus B, 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 1, 0. 1 XOR 0, 1. So here Z is nothing but A XOR B. Apply XOR operation to A, B, then write the resultant. How will you write the state table? You write the symbol. This is 0, S0. 0, 1 means 1, S1. 1, 1 means S2. 1, 0 means S3. And wherever that symbol is there, you write symbolically. So 0 0, 1 0 means S3, 0 0 means S0, 0 1 means S1, 1 1 means S2. So wherever you find 0 0, you replace 0 0 by S0. Wherever you find 0 1, replace by S1. Wherever you find 1 1, replace by S2. Wherever you find 1 0, you replace it by S3. We have learned what is parity checker. Then we have learned how to represent sequential parity checker using state table and transition table and state graph. Next we have learned how to draw state table and state graph for the given circuit.